Alright, sit down, bud.
Oh, yeah, Derek is it. Oh, it is.
Alright, so we talked about the things. Okay, we talked about how bonding, the reason why things bond is for two purposes. Okay, they bond to become stable. Okay, and stable means what from an energy standpoint? But that's how it becomes stable, but from an energy standpoint. Least amount of energy, yes?
I don't even know.
Why don't you just figure that out now?
I'll do it in my back.
Alright, go get them. Okay? Stable. Alright, this is really important because things are going to really start building quickly, much quicker than they have been. Okay? So this stuff is very, very important, and I don't know how much you're really listening to me.
You talk to me. I feel like you're talking to me. You looking straight at me.
Yep. I'm talking to you. Okay?
I'm listening.
So, they bond because they're most stable when they have low energy. And Stephen said what they do to achieve low energy. What was that, Stephen? Okay, that's called a certain rule. What is that rule called? The octet rule, okay? So, why do things bond? To be stable. What does that mean? Low energy. How do they do it? Fulfill the octet rule. Okay? Now there are a few guys that don't fulfill the octet rule. What are they, or who are they?
Elements 1 through 5.
Elements 1 through 5. Hydrogen and helium are obvious because they can be full, have their outer energy level full with how many?
2.
2. Okay? And then lithium, beryllium, and boron are a little bit goofier. There are two ways for them to become stable. Boron has how many valence electrons?
2.
2.
Oh.
3. Why did I say 2? 3.
Oh.
You said 2, and so I assumed you were saying it right. They have 3. Okay? So they could gain 5 to act like neon and have a full octet, or to have a full outer energy level. Or they could gain a full outer energy level by losing 3. But doesn't that leave them with only 2 electrons and acting like helium? Okay? So, 1 through 5 are not going to achieve an octet, but they can still be stable with 2. Right? Sorry, guys. Alright. Then, I introduced 3 ways that they can achieve an octet. Those 3 ways are they can gain, they can lose, or they can share. Okay, now we will talk more about what does what and why they do it. Okay, just quickly laying a foundation of what they can do. Then we talked about something that was very important, electronegativity. And what was that? Yeah?
How strongly an atom attracts electrons?
It's basically like if I show, let's make a really loud ringing noise.
What did you say?
I hit the chair.
Like together?
So we're going to eventually do Lewis structures, which are going to show how hydrogen and fluorine bond. Okay? But believe it or not, fluorine has a stronger pull on electrons when it bonds than hydrogen does. Okay? So what electronegativity is how much, when these guys bond, how much do they pull on electrons? Okay? What are 2 things that both pull strongly? What do you think they're going to do? What if I've got one thing that doesn't pull very strongly and one that pulls extremely strongly? What's it going to do? Okay? So, yeah, essentially, when I said that they can become stable by gaining, losing, or sharing, it has to do with electronegativity. For example, if I bond sodium with fluorine, sodium has a low electronegativity value. Fluorine has a high electronegativity value. So one wants, one doesn't. So what ends up happening is the electron from sodium will go to fluorine. One gives, one takes. And it has to do with electronegativity values. Okay? But what if I have two guys with relatively higher electronegativity values? They can actually attain an octet by sharing, because they both want, and so they will find the middle ground. Okay? Now, I'm getting a little ahead of myself here, but then we talked about how your metals have low electronegativity values, and your non-metals have high electronegativity values. Okay, correct? I had you write that in. Metals, low electronegativity values. Non-metals, high electronegativity values, correct? Okay? What does that mean? When I say something has a low electronegativity value, what does that mean? Yeah, it doesn't have a strong pull on electrons when it bonds. If I say something has a high electronegativity value, what does that mean? It has a strong pull, it wants electrons. Okay? I think this is where we ended, right?
Yeah, the next slide.
Pretty much.
It's like where they're picking up the apples.
Picking up the apples. Okay, so here was the actual electronegativity values. Okay, so you can look. Fluorine has the highest pull or strongest desire for electrons. Francium has the lowest pull. And so what you see is a trend that looks like this. So if I go from the bottom left to the top right, I increase. Generally, as I go straight across, what do you notice? If I just go straight across the period or series, first of all, quick review. What does the period or series tell you? Energy levels. Yeah? But if I go straight across the period, what do you notice with these values? Alright, so no matter what one I'm in, they always get higher. There might be a few exceptions in here somewhere, like there. But, and yeah, there's a few exceptions. But for the most part, as I go from left to right, I increase. And for the most part, as I go top to bottom, usually I decrease. Okay, highest, lowest with that group. There's an exception there, but normally highest and lowest. There are a few exceptions, but for the most part, the trend is as you go top to bottom, you decrease. As you go left to right, you increase. Yes? All right.
So I see RU and then PD.
You see what?
RU,
RU,
PD.
PD. Okay.
What's the difference?
Their electronegativity values, they have the same.
Yeah, okay.
They have the same pull. That doesn't mean that everything that they do is exactly the same.
Yeah, but that's okay.
Alright? Alright? Alright, there are three types of bonds. First type, covalent, and I'm going to add some stuff to this. Well, actually, I'll have you get this in, and then we'll fill out a chart here. Okay. So you can identify what type of bond you have by what's bonding. Remember how I said knowing the metals and non-metals and metalloids and where they're located was very, very important? You cannot know what type of bond you have unless you know where the metals and the non-metals are. Okay? Now, here's what happens with covalent. And I'll have you put this in a separate thing here a little bit later. But covalent, they share electrons. Okay, first off, where are the nonmetals? They're right at the stair step, so they're up here. Generally, what are their electronegativity values? High, low, medium, high. What does that mean? What does a high electronegativity value mean? They want. Okay, so what if, let's say, CO2? We know CO2 is a thing, correct?
Yeah.
Okay? Well, these guys generally have high electronegativity values, so these guys aren't willing to give up their electrons, are they? They both want. Okay? So if they're going to bond, they have to find a happy medium or a happy middle ground where they actually, in this case, they share. Okay, and I'll show you in a sec how they become stable. But look at, this is what the little visual was trying to show you. They're both sharing. Oh, they're nice. Okay? We will do this later. It's called a Lewis structure. Okay? What these bonds represent are two shared electrons. Each dash represents two shared electrons. So carbon, for example, if we were to do the electron dot notation, it would have 4 valence electrons, correct? Could it share 4 electrons? If it has 4 valence electrons, is it possible for it to be able to share 4 electrons? So 1, 2, 3, 4 bonds, it shared 4 electrons. How many valence electrons does oxygen have? 6. Now you're probably thinking, well, couldn't it share 6? Yes, but if it shares 2, won't it have 8? I'm blowing your mind. Each unbonded pair, it can share. So, 2, 4, doesn't this represent 2 and this represent 2, based on what I've been saying? 2, 4, 6, 8. Is there 8 around oxygen? Is there 8 around this oxygen? You're looking really deer in the headlights look right now. Okay, we'll do this later. And I'm just showing you how this works. We're going to get to this much more later. All right? So I'm trying to show you here. Again, I'm going to explain this stuff in more detail when we get into it. Okay? You know, it's not as bad as you think. It is new, but it's not as bad as you think. But what happens is these guys will share to get 8. And the reason why they share is they're not willing to give up because they have what values from an electronegativity standpoint? What'd you say? High. And high means they want. So they're not willing to give up, but they will compromise and share. Now we'll talk about how they can share equally and they can share unequally, but we'll talk about that later. We have ionic. I love this visual. This is my favorite. Okay. In a sec, we'll do a big, not big, but a table that will kind of summarize all this. But ionic, what happens with the electrons for ionic is one gives and one takes. And you can kind of see that based on this particular visual here. Now the question is, which one gives and which one takes? Does the metal give or does the metal take? Why does the metal give?
Because it needs to lose electrons.
Okay. It needs to lose electrons to be stable, yes. It also has a very low what? Electronegativity value. So let me just show you an example. We will also do this in this chapter. Sodium, how many valence electrons does it have? 1. Let's say it bonds with chlorine. How many valence electrons does chlorine have? Okay. Metal, low electronegativity value. Non-metal, what? So, give, take. This creates ions. A positively charged sodium is attracted to a negatively charged chlorine. And that's how they're held together. Now, you're probably thinking, well, how does sodium have an octet if it loses an electron? Well, remember, it has how many valence electrons? 1. If it drops this 1 electron that's in its 3rd energy level, its new outer energy level is now the 2nd energy level, and that should be full. You remember me showing this? I can show it again. Sodium, how many fills the first?
2.
How many fill the second? 1, 2, 3, 4, 5, 6, 7, 8, and we know that it has a total of 11, that's 10. Do you see it's one valence electron so far? If it loses this, what's its new outer energy level? The second, and it has how many? 8. Is it stable? Yes. Alright, starting to put the pieces together a little bit here. I think it's cool. So she's giving the one, notice he's got his 7 here. Everybody see that?
She's giving it, or?
She's giving it to him.
Oh. I thought he was giving it. Yeah, I thought he was giving it to her.
No, passing. Yeah, it's the after effect. She's in love with him.
It looks like.
He has a high, big electronegativity. I don't know if you can tell that. She has a low electronegativity. I don't think. Yeah.
I guess that.
Let's try to show you here.
Michael!
This one's fun too.
Orange to your face. Y'all want some oranges?
So, electrons for metallic. Communal sharing is what they do.
Some of these kids have 4 on
Okay guys, write this in please.
Sorry, what's that orange?
Tell me I turn this on. Yes, hallelujah.
It says that one kid, just in case they have that one. Oh, yeah. That poor child. There's another one too. One of them just doesn't look like he cares. They don't think they're on the cheek.
Alright guys.
They have an orange obsession.
Alright.
It's yellow and orange.
Okay, so first off, let's identify these guys.
Red. 28.
Alright, we're doing grand. Okay, metallic. Is between two metals. So if I just gave you a list of things, potassium bonded with chlorine, would you be able to identify if that was covalent, ionic, or metallic?
Yes.
What is it? How would it bond?
It's the non-metal in
Okay. If potassium and chlorine bonded, what type of bond would form?
that. Ion.
Ionic. Did you say covalent? I think you did. So now we gotta go back all the way back to the element quiz we took and how important knowing some of the names are as well. That's not going anywhere fast either, is it?
If I guess, I'll do.
Okay, so here's what happens. First of all, what do we know from an electronegativity standpoint about metals?
They have a
Oh, low electronegativity values. So it sounds to me like none of these metals really want their valence electrons, do they?
No.
But no one's willing to take it, are they?
No.
So what ends up happening is it's like a communal sharing not by choice.
Right.
So imagine, for example, you guys in your seats are individual metal atoms. And I'm a valence electron. And you're like, I don't want my electron, so you just start passing me back and forth, and I'm just going wherever I want in between all these metal cations that you guys are. Okay? But as soon as I go between these two metal cations, there's probably another electron that's following behind me, because at any given time you'd want an electron in between here. Why? If there wasn't an electron in between here, what would happen? What would these two metal things do? These two positive metal cations, what would they do? What do positive things do to each other?
They
What's the word? You guys know the word?
go apart.
Well, what's the word? It's actually called a specific word. I guess you guys didn't know what magnet was, so. Wait, no, you just wanted me to say it, didn't you? You knew what a magnet was. They repel each other.
That's all I can think of was Appel.
Yeah, I made a joke last year about Appel. Everyone didn't like Appel.
No.
So I was like, yeah, it repels, like Daddy Appel.
Mr. Kramer, I had his mom twice as a teacher in DCA. 4th grade, and 7th grade science.
Was she good? Must have been pretty good. You like science.
We should have 2 different things.
He was in my work
What?
and he broke my leg.
He broke your leg on purpose?
Wait, who
I
broke
don't
your
know,
ring?
I could
Who
probably
did?
not, but he
Mr.
broke my
I
leg.
was in.
Mr. Chappelle?
Yeah.
No, that's.
Why was he using that
Mr.
ring?
Apple broke your
Well, you guys
ring.
are fucking with his rake leaves. I don't know, he was like.
Gotta rake some leaves.
Snapped it.
And he just went.
Oh,
He's like,
Maybe he's just a strong individual.
actually,
Alright. Okay, so here's what happens. It's really quite interesting. Listen. In covalent, they're shared pretty rigidly. Like those electrons aren't moving where they want them anywhere, right? They're kind of shared in between the nucleuses. For ionic, one gives and one takes, and it's pretty rigid. They're not free-flowing. But in metallically bonded things, the electrons are flowing all over the place, in between each individual positively charged metal. Okay? This is why metals have the properties they have. What are some properties we know about metals? Anyone know any properties about metals?
They are good conductors.
Ah, they're good conductors of heat and electricity. And really electricity is the flowing of what? Electrons. So it makes sense why they're very good conductors of electricity, because when they bond, their electrons are already freely flowing. They're freely moving in between all of the positively charged nucleuses. Okay? They're just bouncing back and forth, they're passing to each other, but they don't really want it's like the electron is a hot potato and they're just passing it between each other. They don't want it, but they need it. Did you hear what I said? They don't want the electrons, but they also need the electrons to be in between them at any given time for them to not repel. Alright? Yes? What?
All that stuff.
Oh, I didn't say anything. What are you talking about?
You made the joke.
Well, I was only basing it on what other people said. Alright, ready? Go ahead. I've never had a class with him. I've never.
Oh.
Okay. Alright, here's what I want you to do. Before we summarize all this, I want you to identify what type of bond will form. How do you think you're going to do it? Find if they're metals or nonmetals. And know there are 3 types of bonds. And what type is produced with individual elements bonding. Do you want me to do the first one for you? Alright, do the first one for you. Aluminum. What is it?
Metal.
It is a metal. So metal is bonding with chlorine. What is chlorine?
Non-metal.
Okay, so when a metal and a non-metal bond,
It is ionic.
it is ionic. And what goes on with their electrons in ionic?
They give and take.
Yeah. Now, can someone explain why they give and take from this standpoint? Because this is the next level stuff that I want you to be able to know. Why does the metal give and the non-metal take?
Because the aluminum has low
Because aluminum has a low electronegativity because it's a metal, and chlorine has a high electronegativity because it's a non-metal. So aluminum will actually give 3 electrons, so I'll have to have 3 chlorines to bond with it, which we'll talk about that later. All right, I want you guys to do the rest, and then we'll summarize everything.
Is there any other slides after this?
Nope.
Okay.
But I am going to put the other little chart here. done, Ethan? Draw your head or where'd you put it? Oh, okay. Ooh. There's a noise. You hear that? Play that. It's like a tuning fork.
Oh, I ran.
Dunkirk?
No, Doctor Who.
Oh.
That's a movie. We need to do all of them. Dunkirk is good.
Yes.
Oh, why she's back?
Everett? Still working? Moira, done?
Yeah, I don't know.
Shane?
Right too slow.
I don't remember.
Can't find them? Okay, you're gonna get to the point where you guys are going to be real familiar with your little boyfriend and girlfriend up here, right?
What?
I might have to even say PDA a little bit, you know.
PBA. Wait, hydrogen is a non-metal.
Hydrogen is a
Well-
non-metal, yes.
Hydrogen.
It is an exception. Were you gonna try to play a trick on her?
No.
Oh, it's left to the period, left to the stereo.
Ooh.
But technically,
Well,
it's technically not attached. Because it's like above.
Yeah.
So you could say,
Well, it's a gas, so it is floating around.
That's true.
Oh, that's so funny, but I don't know
All
why.
gases are
So
like,
alright, okay?
right? It's
Mari.
12.
Actually, Marty, you did the first one, so.
Wow.
Rose, could you tell me, carbon and oxygen, when they bond, what type of thing will they form? What type of bond? What was that? Covalent? I think, yeah, covalent? Okay, what goes on with the electrons in covalent? Share, and it may be equal, might be not equal, we'll talk about that later.
You don't want us to regulate
Nah, I didn't actually do that,
it.
but I'm doing that just to so we see it. Edith, lithium and sulfur.
Ionic,
Now, why is it ionic?
because lithium's a metal and sulfur's a non-metal.
Yep.
How
Metal. How ironic, ionic.
Most bad. They have ionic superpowers.
Okay?
Oi,
Miss Node.
oi,
Next one.
oi, oi.
Metallic. What?
I thought sulfur was like, AKA brimstone.
Yeah.
That's the Bible
So ain't that,
representation.
so ain't that a metal, no, or whatever?
Yeah, sulfur's not a metal.
Cobalt.
Ain't it a what?
Cobalt is a metal.
Nothing.
Sulfur is just referred to as brimstone in the Bible.
So it's not really brimstone.
It's not made of stone. That's yeah. Brimstone doesn't mean it's made of stone. Okay. Hydrogen and oxygen. Sid.
Covalent.
But I thought this guy was left to the stair step.
But he's an exception.
Okay.
He's a part of the
Yeah.
power.
Alright, I'm not gonna continue to keep writing what they are here.
Thank you.
Alright. Moira. Cobalt, zinc. Metallic. Metal and a metal. Shane.
Yes.
Calcium and fluorine.
Ionic.
Ionic.
Yeah. Ew.
That's
Kind of
ironic.
ionic that they're paired together.
Okay. Now, this is a good way to identify it. Can you explain from an electronegativity standpoint why ionic give and take? Can you explain from an electronegativity standpoint why covalent share? Can you explain from an electronegativity standpoint why metallic, they kind of share by not wanting to? Okay? So, here's what I want you to finish. What?
That's fine.
You hit yourself in the head?
Yeah.
With what?
With my
The
this.
string.
The metal.
We're doing I have a habit of chewing
Yep.
on mine.
Okay.
I did this one.
First thing, bond type.
Is it a big star difference?
Let's know.
First of all, what is there are how many bond types?
3.
Okay, first one,
Covalent.
No.
okay, next one,
Ionic. And then metallic. Yeah.
Okay, so there'll be 3 or 4 rows. Okay, how to identify. So what do you think I'm asking here when I say how to identify?
By what type
So
of
that
item,
showed these.
elements or bonding?
By what elements are bonding and what they are. So covalent, you can identify as covalent if it's what?
2 nonmetals.
Ionic, I can identify between what?
Metal and non-metal.
And metallic,
2 non-metals.
to what?
Metals.
Right? Electrons. What's going on with their electrons? Covalent is? Ionic?
Nucleic.
And metallic. This might be some of my best writing. So neat. Let's do an example.
This is the last one.
Yeah. Let's do an example. Let's start with something simple.
Green.
Let's say, let's just do this real quick. Let's say oxygen bonds with fluorine, right?
Okay.
Oxygen has a high electronegativity value. Fluorine also has a high electronegativity value. So this is why they share. I don't know, I maybe should have done that first. Okay, they both want lithium with, let's say, chlorine. Lithium has a low electronegativity value. Fluorine has a high electronegativity value. This is why they give and take. Does it make sense? Let's say iron with, just say another iron molecule. Low electronegativity values. None of them want. That is why they communally share by not wanting them. Alrighty?